am Harish and I am going to give a presentation on verification by model checking. So in this talk I am going to cover the following topics, that is modification for verification, LTL logic, model checking and CTL. So let's begin with modification for verification. That is why we need to do verification of the systems which we design. First one is the checking of correctness of computer systems, whether they are hardware, software or a combination. For example, we need to formally verify whether the safety critical systems are working correctly or not, or commercially critical systems are working correctly or not. Now the formal verification techniques can be thought of as comprising of three parts. First one is a framework for modeling systems. Typically it is a description language which is used to model the system. Second one is a specification language for describing the properties to be verified. Third one is the verification method to establish whether the description of the system satisfies the specification or not. Now let's see what are the different approaches to verification. First one is proof-based versus model-based. In proof-based approach, the system description is a set of formulas and a specification is another formula, and the verification method consists of trying to find a proof that satisfies the formula with the given specification. In model-based approach, the system is represented by a model M for an appropriate logic. The specification is again represented by a formula phi, and the verification method consists of computing whether a model M satisfies phi. The second one is degree of automation. The degree of automation approaches differ from how automatic the method is, and there are mainly two levels of automation. First one is fully automatic and another one is fully manual. Third one is full versus property verification. The specification may describe a single property of the system which has to be verified, or it specifies the full behavior of the system that is to be verified. Next one is intended domain of application. In the intended domain of application, it may be a hardware or software, or a sequential or concurrent systems, or reactive or terminating systems. A reactive system is the one in which it reacts to the environment or is not meant to terminate. Examples of reactive systems are OS, embedded systems and computer hardware. Next one is pre versus post deployment. Verification of great advantage if introduced early in the course of system development, because errors caught early in the production cycle are less costly to rectify, and hence pre-development is always recommended than the post-development. Now, model checking is an automatic, model-based property verification approach, and it is intended to be used for concurrent reactive systems, and it is originated as a part of post-development methodology. Now, formal verification can be done using the Ally or with the model checking. So Ally system is automatic, model based property verification approach, and Ally finds the models which form counter examples to assertions made by the user. That is, Ally doesn't check whether the assertions made by the user are correct or not. It just checks in which models these assertions are false. If any of the models in which these assertions are false, it will report those models. Now the model checking starts with a model described by the user, and it discovers whether hypotheses asserted by the user are valid on that model. If it is not, then it produces the counter examples consisting of execution traces. That means that in model checking, whatever model we specify, only in that specified model it will check whether the assertions made by the user are valid. If not, Then it will form the counter examples of consisting of models. Now another difference between the align and model checking is that model checking focuses explicitly on temporal properties and the temporal evolution of systems. Now model checking is based on temporal logic, and the idea of temporal logic is that a formula is not statically true or false in a model as in the propositional or predicate logic. It means that in temporal logic we will incorporate the view of time, and since incorporating a view of time, the logic can be true in some states and it can also be false in rest other states. So instead the models of temporal logic contain several states and a formula can be true in some states and false in others. In model checking, the models M are transition systems and the properties psi are formulas in the temporal logic. To verify that a system satisfies a property, you must do three things. First one is model the system using the description language of the model checker, arriving at a model M. And we need to explicitly code the property using some specification language given in the model checker, resulting in a temporal logic. And then we will run the model checker with the inputs as the model which has been described using the description language and the specification language which is used to code the property to be verified. Then once we run the model checker will output the answer either yes if this model satisfies that specification or no otherwise. Now temporal logics are classified according to their particular view in time, and based on this view of time there are mainly two types of logics which are used to code the specification. One is the linear time logic, which represents time as a set of individual paths and they are independent. Second one is the branching time logic, which represents time as a tree and the root is the present moment and the subtrees are the branches which point out into the future. First let's see what is the linear time temporal logic. Linear time temporal logic models time as a sequence of states, extends infinitely into the future. The syntax phi of the LTL logic is given by true or contradiction or any proposition or negation of phi, phi and phi, phi or phi, phi implies phi, x of phi, f of phi, g of phi, phi until phi, phi weak until phi, and phi releases phi. So in LTL we will incorporate 5 temporal connectives which represent time. First one is x, which represents next state, f represents some future state, g represents all future states globally, u represents until, r represents release, and w represents weak until. And we have a convention which is used to bind the connectives with connectives. So it states that the unary connectives consisting of negation and the temporal connectives f, x, f and g bind most tightly. Next in the order comes until, release and weak until. Then comes and or, and after that comes implies. Now following are the examples of some LTL formulas which are valid. In the first column we can see that the formulas are written using the parenthesis, and in the second column we see that the LTL formulas which are similar to the first columns but without using the parenthesis, since we can very easily know that using the binding properties we can figure it out that both are equal. Now let's see what is the past of an LTL formula given by, for some future state, P implies G of R or negation of Q until P. The figure shows the pass tree of the given LTL formula. In the root node is OR, since it binds at the last. Negation binds close to the given proposition, and hence negation binds to Q until binds next to the negation, and hence negation of P until P forms one subtree, and for some future step P implies G of R forms another subtree. Combining these two subtrees using the OR gives the pass tree for the LTL formula. Now let's see the semantics of LTL system. A transition system models a system by the means of states and transitions. That is, in LTL logic, these can be represented using states and transitions. And we have a definition which states that a transition system M is equal to S implies L is a set of states S endowed with a transition relation, that is implies, which is a binary relation on S, such that every small s belongs to S as some small s belongs to S, with S implies S and a labeling function L which states S implies P, that is P is the utterance. It means that L of S means a set of atomic propositions which are true at that particular state. L is just an assignment of truth values to all the propositional atoms, and since system has many states, the assignment depends on which state S the system is. And the requirement that for every S belongs to S, there is at least one S dash belongs to S, such that S implies S dash means that no state of the system has deadlock. If a system did deadlock, we could always add an extra state SB representing the deadlock together with new transitions S implies SB for each S which was a deadlock in the old system, as well as SB implies SB. Now this figure shows a transition system which has a deadlock at state S4 since it has no outgoing edge. So system at state S4 is in deadlock state. In this case we add another state SD where we show the transition from state S4 to SD along with a self transition from SD to SD to represent the deadlock in the system. Now let's see what is the definition for a path in a model. A path in a model M is equal to S implies L is an infinite sequence of states S1, S2, S3 in S such that for each I greater than or equal to 1, Si implies Si plus 1, and we write this path as S1 implies S2 implies so on. Unwinding the system state graph into the infinite computation tree. This helps us to, unwinding the system helps us to analyze the progress of the system as and when some transitions occur. Now let's look at another definition. Let M is equal to S implies L be a model and phi is equal to S1 implies S2 so on be a path in M, and we need to check whether phi satisfies an LTL formula is defined by the satisfaction relation, which are as follows. Phi represents the path starting at the state S1, or it can start at any state given in the unwinding of the tree. So here is an illustration of until. So there is a transition from state S0 to state S10, and P until Q, it means that P will remain true and in all the states till the state S9, and once the state S9 becomes true, that is when Q becomes true, the state of P afterwards is undetermined. That is, we can't say what is the value of P, that is either true or false after state S9. Now let's see some of the important equivalences between the LTL formulas. And we say that the two LTL formulas phi and psi are semantically equivalent or simply equivalent, represented by psi symmetrically equals phi if for all models M and all paths phi in M, phi symmetrically entails psi and phi symmetrically entails phi. One of such equivalence is whole negation of phi and psi is equal to negation of phi or negation of psi. That means negation is distributive over and negation is distributive over all. Now the next set of equivalence is F and G are duals of each other and X is a dual with itself. That is, negation of G psi is equal to F negation phi, and F phi psi is equal to G negation phi, and negation of X phi is equal to X negation of phi. Another set of equivalence is until and release are duals of each other, and the equivalences are shown. Now another set of equivalences are F distributes over and or and G distributes over and. That is, F of phi or psi is equal to F of phi or F of psi, and G of phi and psi is equal to G of phi and G of psi. Some other equivalences for until, weak until and release are shown. Now let's see adequate sets of connectives for LTL. Set true and a negation forms an adequate set of connectives since the other connectives or implies and true can be written in terms of these three. Now X is completely orthogonal to other connectives. That means it just doesn't help in defining any of the other ones in terms of each other. And each of the sets until and next state, release and next state, weak until and next state are adequate, because release and weak until may be defined from until, and until and weak until may be defined from R, and R and until may be defined from W, and based on the previous equivalences which we have defined and the duality rules. Now let's see model checking by NUSMV. NUSMV provides a language for describing the models, and it directly checks the validity of the LTL and also the CTL formulas on these models. SMV takes as input a text consisting of a program which describes a model and some specifications which are the temporal logics, that is LTL and CTL, and it produces as output either the word true if the specifications holds, or a trace showing whether the specification is false for the model represented by our program. Now, similar to C or Java programs, SME programs also consists of one or more modules, and one of the modules must contain main module. Modules can declare variables and assign to them, and assignments usually give the initial value of the variable, and its next value as an expression in terms of the current values of variables. Now this code is a sample example of NUSMV code, which is a main module, and it declares two variables, request and status, and it assigns the value for status. First statement is the initialization of status with the value ready, and the next status is an expression which is a case statement. LTL specification might also be specified in the program with the keyword LTL spec. Now let's see what is computational tree logic. Before going to that, let's see how we run the NUSMV. NUSMV is normally run in batch mode from a Unix shell or command prompt in Windows. The command line running NUSMV is NUSMV filename.smv, and if we want to run the NUSMV code in interactive mode, we have to enter the command NUSMV -in followed by the file name, so that we can run it in its NUSMV's own command prompt. Now let's see what is computational tree logic. It is also called as a branching time logic. Means that its model of time is a tree-like structure in which the future is not determined. There are different paths in the future, any one of which might be the actual path that is realized. Now let's see what is the syntax of CTL. We define CTL formulas inductively using the bracket norm form as we specified it in the LTL. The syntax is as given. In this syntax, we will find two new alphabets. One is the capital A and capital E. Capital A means along all paths, and capital E means along at least there exists one path. Now we have a convention for binding the temporal connectives for the CTL formula. The unary connectives, that is the negation, and the temporal connectives AG, EG, AF, EF and AX, EX bind most tightly. Next in the order comes and OR, and after that comes implies AU and EU. AG of Q implies EGR. Some of the LTL formulas which satisfies the binding properties are listed. Now let's see an example of the parse tree of the given CTL formula. As specified, negation binds most tightly, followed by AND, then binds the temporal connectives EX, followed by EU and AX, and at the end the two subtrees are combined using the connective AU. Now a model M in CTL is M is equal to S implies L for CTL connectives of a set of states S, a binary relation which implies on S, such that for every S belongs to S there exists S dash which belongs to S, with S implies S dash, and a label function is also defined in the model, which is given as L to the S implies P, where P are the atoms, that is propositional atoms. The intuition is that L says which atoms are true in the state, and implies describes how the systems move from state to state. A graphical representation of the system is shown with a set S of three states S0, S1, S2. A labeling function L of S0 means that at state S0 the prepositional atoms P and Q hold true. At the state S1 the prepositional atoms Q and R hold true, and at the state S2 the prepositional atom R holds true. The implies is a binary relation which defines two states. The transition states are S0 to S1, S1 to S0, S0 to S2, S2 to S2 and S1 to S2. Now, model M is a binary relation which connects the states and has a labeling function, and S belongs to S and finds the CTL formula. The satisfaction relation in which the primitives are M and S, we need to check whether it satisfies the given formula phi, and it is inductively defined as below. These are some more conditions which we need to check. Now, the slide shows some of the basic connectives and their corresponding meanings. E, F, psi means that in a unwinding of a tree, one particular path will satisfy the LTL formula at some future state. E, G, psi means that there is one particular path in which all the states will satisfy the particular LTL or CTL formula. A, G, psi, it means that all the paths and all the states of the paths will satisfy the LTL formula. A, F, psi, it means that all paths will satisfy the formula given only one state in the path will satisfy the formula. Now let's see some of the important equivalences between CTL formulas. Two CTL formulas phi and psi are said to be symmetrically equivalent if any state in any model which satisfies one of them also satisfies the other. We denote this by phi satisfies psi. Some of the equivalences of CTL formulas are listed. Now this slide shows some more equivalences in the CTL. Now let's see what are the adequate sets of CTL connectives. AU, EU and EX form an adequate set of temporal connectives, and EG, EU and EX form an adequate set, for we have the equivalence as defined below. Then AG, AF, EF and EG can be written in terms of AU and EU. Therefore, AU, EU and EX form an adequate set of temporal connectives. This concludes the presentation on verification by model checking. Thank you.